Hello everyone, and welcome back to the series on intermediate statistics. Today we're going to be talking about a very useful method that can be used when you do not know the distribution that you're sampling from. Now, why do we care? So suppose you have a simple random sample S drawn from some population and you actually don't know the distribution of that population. That means you don't know its normal, you don't know its uniform, you don't know its exponential, you don't know anything about its shape and structure. Now, this is important because a lot of the tests we use, at least in basic and some intermediate statistical theory, are usually parametric tests. For example, the F test for multiple linear regression, or maybe the T test for the value of a mean, or the Bartley test for the homostochasticity between two or more populations. They usually require some structure of that population, for example, normality, or not skewed, or it's bounded, or it's of some particular shape. Right? Now, sometimes we can get away with not knowing the distribution of P. For example, let's assume that we're doing hypothesis test on the mean of a particular population, because usually what we do to estimate the mean is we use the expected value of x bar, because x bar is an unbiased estimator of the mean. So we don't necessarily know the distribution that this mean is associated to, but we want to, say, build confidence intervals for this particular means, right? So usually we have a confidence interval for the mean of the structure, x bar minus some margin of error and x bar plus some margin of error, and usually that margin of error takes the structure of, a critical value times the standard error of the estimate, maybe a finite population corrector, maybe some other things as well. But if you do not know necessarily that the distribution comes from a normal, then theoretically the test statistic that we usually use, which is usually of the form x bar minus mu 0 all over the standard error, usually is not going to follow a z or a t distribution, even if you do know the sample distribution or know the population standard deviation or not. So usually what we can do is, well, there are some theorems that say, well, if the sample size is arbitrarily large, maybe this test statistic, which is z, actually converges to a z distribution, as long as n gets arbitrarily large. Keep in mind, if x does not come from a normal, this test statistic will never be normal, no matter how large the sample size is. A lot of people usually say 30 is a good sample size, but 30 out of 5 million people is not large at all, right? But, one thing that is important is that this test statistic does converge to a z distribution the larger and larger n gets. So as long as you're willing to accept that error, and the difference between the distribution that you have and the asymptotic distribution that you want, then sometimes that's okay, and you can usually inflate your alpha by a little bit to sort of offset that difference. And this is obviously the central limit theorem and the common misinterpretations of it. But generally speaking, we need to know the distribution of the population that we're coming from to sort of see, okay, well, this distribution that we're sampling from this average appears sort of normal. So the central limit theorem should guarantee convergence to normal as long as our sample size is relatively large. Or we can say, well, our distribution that we sample from doesn't look anything like a normal distribution. So the central limit theorem guarantees that we need a sample size of at least 5 million in order to get anything sort of normal, right? So we can sort of start to have those conversations if you have some idea of the distribution that you actually are sampling from. Now, there are tests out there to sort of test the distribution that you're potentially sampling from. For example, you can do a Lilliefors test. So you can do a Lilliefors test. Let's assume you could also do a Kolmogorov-Smirnov variation on that. So let's sort of recall what that is. So we take a sample and then we z-score that particular sample so it has a mean of 0 and a standard deviation of 1. And then we look at the cumulative density for a truly normal distribution, which is of that shape. And then we look at the cumulative distribution of our z-score distribution. And then, of course, we're going to have a increasing curve, but we're going to have something like that. So if this is going to be a Kolmogorov-Smirnov variation, then we're going to look at the maximum differential between these two curves and see if that's arbitrarily large. Keep in mind, the CDF is bounded between 0 and 1, so, is that distance close to 0 or 1 or not? You could also do the Kremer-Von-Mises or an Anderson-Darling variation as well if you're interested in doing so, right? So when you see this type of picture, what you have is evidence of non-normality, because there's always going to be some difference between your empirical distribution and the theoretical distribution that you're testing against, right? But keep in mind, generally speaking, if it's not normal, and it never will be precisely normal, what type of distribution will we have? right? So we have evidence of non-normality. We also, in some sense, have evidence of normality if you have evidence to prove that that Kolmogorov-Smirnov test statistic or others are relatively small. But one very important thing you need to know is the following, is that our sample always provides evidence. Always provides evidence of some distribution, even if you don't know what it is. So the natural question that we need to ask, which one is it providing evidence in favor of? So the method that is used to sort of build or estimate this probability density is what we call bootstrapping. So bootstrap samples or bootstrap sampling can help us with this. And that's the method that I want to talk about today. So how does a bootstrap method take place? So let me list out the steps. Step 1. So step 1, what we're going to do is we're going to obtain our sample S of size, let's assume n. And this could be small, this can be large, you get the best sample that you can get. So once you obtain your sample S, which we usually have, the next thing that we're going to do is we're going to obtain several samples. And when we say several samples, I mean like 10,000, 10 million, something like that. And then we're going to obtain the samples of size n from S. Now, you might be thinking, well, if I obtain a sample of size S from my sample of size S, isn't that the same exact sample each time? You would be right. So what bootstrapping does is it allows replacement with replacement, right? Keep in mind our sample does have variance, it does have central tendency. So if it does, for example, have a bimodal structure, we should have a bimodal empirical distribution for all of these samples. And these samples that I mentioned here are usually referred to as bootstrap samples, right? The more the better. And then, once you have your bootstrap samples, 10 million of them, then what you're going to do is you're going to calculate your test statistics and confidence intervals from them. So calculate whatever metrics you want. So calculate your metric from all the bootstrap samples. And in terms of the metrics, you could, for example, look at the mean, you could look at the variance, you could look at confidence intervals for the mean, and so on. Depends on what you want. Now, you might recognize that the structure is very similar to a Monte Carlo simulation, but Monte Carlo simulation and bootstrapping methods are completely different and unrelated tests. So bootstrapping is aiming for trying to build the empirical distribution that we have from our sample, that our sample was drawn from. So we're trying to estimate the distribution of P. But a Monte Carlo simulation does not require anything or any samples, so it's trying to build the actual theoretical distribution of, say, a test statistic, for example, like the Kolmogorov test statistic, or maybe some more complex test statistic that you never really have the chance to build the theory for. So Monte Carlo is more on the theoretical realm, and bootstrap sampling is sort of on the empirical realm, but it's trying to estimate something that is indeed theoretical or parametric. Right? So that's pretty much what we are going to do, and I will actually go through in our simulation of how to actually do a bootstrapping sampling structure. But before we get into that, our demonstration, I want to mention some very important caveats and things that are very important to understand before you actually decide to use or not to use a bootstrapping sampling method in your statistical analysis. So here are some of the things that the bootstrapping sampling method does do well. Obviously, it does estimate sampling distributions, which in some sense is what it's designed to do, right? Because it draws from that sample and it pretty much uses all of the metrics, for example, the mean, the variance, the skewness of that sample, and tries to recreate the distribution for which it comes from. Right? But keep in mind, if it does not cover the entire range, or your sample does not capture your true shape of your population, your bootstrapping samples will carry that bias and error with it, right? So those two things are very important to keep in the back of your mind. Also, constructing your confidence intervals with n and small is also very, very good. Because what you have here is you have your sample, which comes from your distribution. In your sample, you have your test statistic, and what your bootstrapping samples are is approximating your sampling distribution, and that sampling distribution is in some sense indirectly giving you those samples, other samples out there, with similar but not necessarily equal to itself confidence X bars, for example, and you can build confidence intervals from all of those X bars, even if your sample size is small. But again, if your confidence interval is based on a sample of size n that is small, then it can still give you that bias and error issue that you already mentioned. Also, technically it assumes that your data is independent and identically distributed, which is definitely not true when you're working with time series data, because usually as time changes, the parameters for which you're estimating are also changing as well. So it's very important to keep those two things in mind when interacting with each other. And also, since we're not assuming anything about the population distribution, and in some sense we're trying to create it, bootstrapping sampling methods can definitely be helpful when you're doing non-parametric testing, when you actually don't want to assume the distribution, or you have evidence to believe the distribution isn't normal or something like that. So that's very, very useful. Also, if your sample does by chance observe something that is extremely rare, when you bootstrap those rare events, what you're actually doing is making it seem like those rare events are actually more common than they actually are. So that's another thing that you need to keep in the back of your mind when you're doing bootstrapping sampling. A couple more things that you definitely should know is things that bootstrapping should definitely not be used for, and I have seen several resources where they actually do these things, so be very, very careful. If you have models, for example, confidence intervals for the population mean, where the theory is well established, where it's very common knowledge in the statistical society, to do certain things, do not use bootstrapping methods for those particular models. In one sense, you're losing statistical power to reject things that are actually false. And a lot of people, when they don't get the results they get from that fully built theory, usually they go to bootstrapping methods because they really do believe that their sample is wonderful and amazing, and it usually gives them p-values that are a lot lower than they actually would have gotten if they used the actual built theory. Another thing that I see a lot of people do is they inflate their sample sizes with your bootstrapping samples. That is, when you take your bootstrapping samples and you put all of those bootstrap new values, which keep in mind are the same exact values from your sample, they put those sampled values into your original sample, and you're pretty much replicating your data. Keep in mind, if you have error or bias in your sample, when you bootstrap sample from it, you will carry that bias. So if you inflate your sample size, which yes can make your p-value closer to 0, and you can reject null hypothesis more often, you are also inflating your bias, you're also inflating your error, which will definitely get you into a lot of ethical trouble if you decide to follow that. If you want to make your sample size bigger, go out and sample more people, but do not replicate your sample for those reasons. Also, bootstrap sampling is not repeated sampling from your population. It's repeated sampling from your sample, which is very, very different, because if your sample has bias, then your bootstrap samples will also do. Some people think, oh, if they bootstrap sample, it'll make your p-value smaller, and that means, the probability that we are wrong is actually lower. That's not true. That's not even true for one sample for confidence intervals, right? So keep that in the back of your mind. So just because you were not able to sample more people from your population, bootstrapping will not help you to overcome that for the reasons that I've already mentioned above. And there's one more category that I actually do want to mention in terms of some other observations that I think are very important to note. And this actually can help you interpret what your bootstrapping methods actually are. So if your p-value for your original sample and your p-value associated to your bootstrapping samples are both small, then this is actually very good for rejecting the null hypothesis, right? So for example, if you get a small p-value for your sample, then you probably wouldn't be using bootstrapping methods anyway. But if you sort of want to make extra sure that your results aren't right only by chance, then you might want to do some bootstrapping methods to sort of simulate that. particular statistical study. And if you get p-values that are small for both, then it's actually very good for you, right? And the alternative to that is if your p-value is closer to 0 and your p-value for your bootstrapping samples is not close to 0, then what this actually means most of the time is that your sample results usually are only good by chance. So likely occurred by chance. So, some people will be like, oh yeah, I did a p-value and I got something close to 0, but then I did a p-value and got something far from 0. I'm going to publish my result anyway because it's less than 5%. Definitely don't do that. That's unethical. Because maybe if you select actual samples from your population, which you definitely should do, then you probably will likely get different results that might not be statistically significant compared to your first sample. Now that we've discussed all those little ethical things and what bootstrapping method is and what it is not, let's actually get into our demonstration of how to actually do one. So what I'm going to do is I'm going to generate an artificial data set that definitely doesn't come from a normal distribution. The reason I say that it's not going to come from a normal distribution is because I'm going to merge two different distributions with two different means, and I'm going to make a bimodal data set. So I'm going to set seed for reproducibility, so just in case you want to copy these data values. So once I give these two values and then I concatenate those data sets together, if I do a histogram of these particular values, as you will clearly see, we're going to have a bimodal data set, one on the left by 3 and the other by 5. So clearly this is not going to be a normal distribution, and you should be able to verify that with, say, a Lilly-First test statistic. So when we have this and we see that particular thing, what are we going to do about confidence intervals? For example, if we don't want to use that particular, a t-test for the mean. Now, we could invoke central limit theorem and make n be arbitrarily large, but let's assume we didn't actually have a chance to get 5 million data values for our sample, and we only managed to get like 40. So what are we going to do for that? Because we clearly can't use the t or z critical value for that. So bootstrapping method would be useful here. So let's assume that we actually want to estimate or construct a confidence interval for, say, the variance or the mean, or maybe we just want to construct a confidence interval, for particularly any metric at all. So let's actually look at the x-bar values, and let's actually look at the variance values as well, and I'm going to store them in each of these vectors. Now the simulation setup for this is actually very similar to a Monte Carlo simulation, but keep in mind Monte Carlo simulation and bootstrapping are completely different from each other. So what I want to do is let's assume I want to do 10,000 iterations, so that's going to be our for loop setup. Then my simulated sample is going to be as follows. So keep in mind, bootstrapping will sample from your data set of the same exact sample size, and we will be using replacement. Right? So once you have your simulated sample, then you're going to calculate the mean of that sample, and let's also calculate the variance of that sample. And I want to look at the distribution of these particular statistics. Let's assume that that's what you're actually looking for. So my x-bar vector is going to be updated, so my x-bar by that first value, and then my variance vector is going to be updated by that new value too. Once I give that a run, so let's just click all of this and run it. Then we're going to have our little stop sign, and then it's going to run, and that's going to give us our two vectors, both of size 10,000. So if we look at the histogram for my x-bar, we should see something that sort of looks like normal, and that sort of comes from the central limit theorem. So we're going to have, let's add some colors to this. So color equals light blue, and since we have 10,000, let's force the particular number of breaks to be something like 250. And let's also look at the histogram for my variance, and let's assume we also want to use, let's do light pink, and what's this 0 doing there? And then we're going to do breaks is equal to 250 as well. And let's not forget our comma after our color command. So that's going to generate the first histogram. And look, it looks sort of normal. Let's look at our histogram for our variances. Also looks kind of normal, but you already know that the variances should look at least sort of like a chi-squared distribution, because none of these values can be negative, so it can't be normally distributed, at least theoretically. right? So once you have these, then what can you do? So let's assume that, for example, you want to make a 5% alpha two-tailed confidence interval for the population mean. So our alpha value would be 5% in that case, and it's going to be split into two tails. It's going to be a confidence interval for the mean of the population, which we don't know actually. In fact, it's coming from a bimodal distribution, so our traditional sampling techniques cannot work, so bootstrapping method very useful here. And let's assume we want to use bootstrapping for this confidence interval generation. So once you have the distribution associated to the test statistic you're interested in this case x bar, then our confidence interval is going to be, so the lower bound will be to the lowest quantile, so it's going to be my x bar, and then that's 0.05, or alpha, over 2, and then the upper bound will be equal to the other quantile, so my x bar, then 1 minus alpha over 2, and that's going to give you the upper quantile. And then we can look at the confidence interval, which is going to be lower bound and upper bound, and that's going to give us our values. So once you give those a run, which obviously doesn't look correct, and let's see what we did here. Well, it seems like we rounded to the nearest integer. Let's assume that we want to round to 4 decimal places because a confidence interval from 4 to 4 is actually quite useless. So if we just change that to 4 decimal places, then we have evidence to believe that the mean is in between 3.7 and 4.3. And if we go back to our sample generation, we had a mean of 3 and a median of 5. We would expect the mean of this bimodal distribution to be somewhere between the means of these two bimodal normal distributions, right? And we can do that for literally anything, including the variance as well. So if I want to create a confidence interval for the variance, I would just change that to my var, and then my var, and then update those things. So here we have evidence to believe that the variance of our original bimodal population is somewhere between 0.9 and 1.2. And those would be bootstrap confidence intervals, and we can adjust this alpha as usual. So, hope you enjoyed this video where we introduced the idea of bootstrapping methods and discussed some of the pros and cons of this method. Hope you enjoyed, and I'll see you in the next video. Take care.